Hey everybody, welcome back to Hired Labs Coding Bootcamp week 2. We're going to talk about algorithms and data structures. We're on day 4, so we talk a little bit about algorithms. We haven't talked about data structures specifically. We're going to spend some time a little bit defining that today, but mostly what today is about is evaluating them and how we make a decision between one and another, what choices we're making, what it means when we make a choice, and then what we're affecting with the choices we are making. With that, we sent out a problem set. I know a couple of you got some chance to do anything. Anybody that I hadn't talked to already get a chance to work on a few of these yet between last class and now? No.
I I had to dip the last time, but I got it
Okay.
on an hour ago and started working on these, and that code Code Wars is fantastic. I clicked your first lesson and I realized I didn't even know how to multiply because we did it and it was so easy. I think I dumped it, so I had to go back and learn it. But yeah,
Nice.
that's a great homework stuff, man.
Yeah, cool. And so the thing there is once you get into it, and when we showed last time was once you solve a problem, you can see other people's solutions to it, and you see how many different ways there are to solve it. So what we're going to talk about today as one of the main topic, and what we want to get through today is how we decide which one is the best. Like, what is the best solution? Is there a best solution? How do we determine that? Right. Um, so anybody have any questions before we move on about that? Anybody have any questions specifically about the problem set or stuck somewhere that you wanted to kind of chat through real quick? 'Cause we got some time. We could talk about it if you had a thing. No. All right. Cool. So let's just do a quick review of what we've done up to now. And it's not going to be comprehensive review. It's going to be like, when you're watching a series or something and they say previously on, and they just talk about what's going to be relevant to the show you're about to watch. So that's kind of what we're going to do now. So we talked at one point about the difference between human and machine languages, and we gave this chart shows the languages at the top, Python and Ruby, JavaScript, those sorts of things are much closer to human language, much closer to English. We've seen that now. We've done some of the syntax. Um, but the reason I'm bringing this up now, and I remind us of this, is because we're going to be talking about the tension between these things as being a constant decision we're making on how we write our code. So we did a little bit of refactoring at the end of our last class. And who remembers what refactoring means and what we did when we refactored?
That
Anybody
was
recall that?
what rewriting the code to make it more efficient, going through a different way of finding the problem.
Yes, yes, rewriting exactly. So rewriting code. So rewriting code is getting at this. So in some way, we're making it either easier for humans to read, or like you said, more efficient in a way that where it's going to be faster or whatever, right? So there are a number of ways that we decide this. We're going to talk about how the decision is made, but this is one of the things that we're always keeping in the back of our mind, and we're always making a decision between the human readability and the machine readability of it, because there's a cost in energy and time coming from the higher levels of this chart up towards Python down to machine learning or machine language in the binary level. All right. So then again, as review, we've talked about data a few times. We're going to talk about data structures today. So I want to be clear on what we've talked about data and how it is going to be related, but we're going to talk about it in a slightly different way today. The first way we talked about it was in terms of bits and bytes and how data is stored in memory and how it's used by the computer to understand what we're talking about. If you recall, this is a capital N according to our ASCII chart. And we need to keep this in our mind as well today when we're talking about how we decide things and how things are moved in the memory of a computer. We're going to be picturing this right here, this space of bits and bytes being physically set aside places, and how the things that we do in our code will affect the computer's ability to move them around and understand them. So data in sense of binary is one way we talked about it. And the next way we talked about data was data types, specifically in Python. And who remembers a couple of data types? Anything we remember? What are data types?
Strings, integers,
Yep,
tuples,
very good.
lists.
Exactly. So we had all the things that we can write, sort of group these somewhat arbitrarily, kind of my own grouping, things we write in literals, right? So strings, like you said, integers, floating point numbers, so anything with a decimal, our Boolean values, the true and false. Then we have our collections of things, so our variables, lists, tuples, sets, dictionaries. Then we got the functionality, we have functions, and then groupings of all of that in classes with their attributes and methods, right? So we've talked about data in this sense of the way that we group Python syntax, the way Python allows us to group objects together to communicate with the computer, right? So what we type here to create something like a float or something like that, the computer understands it as this type of data and can do certain things with it. Right? Okay. And the last thing that I want to make sure we highlight as review is something that's going to go throughout the course is that all programs are files in directories. So we've been running our own files out of directories. This is, again, the example of a Linux file system. Got our home, our slash, our root, and then the home, and then the user, and then our working directory where we are. We're going to go over to Python Anywhere from there and go through the quick where we ended up last time. Let me get out of this real fast. And I'm just going to go into a console real fast, and we're going to look at our two files that we ended up with for connecting this and running it all together. So first, I'm going to do ls to list what we have here in our home directory. And don't worry about these, my site and VM. I spun up our example site for later today if we show for what we're going to be doing next week. But we should have finished up with a main.py and our classes.py. Recall, let's go ahead and run, I'll clear this up. I'm going to run cat, which is a way just to read something in a file out here on our standard output without opening that file. And I'm just going to have a look at what's in our classes for review. So if you recall, we defined our car class in here with a couple of methods, which are functions that are inside of a class. And then who remembers what data type this args is? What data type is this?
That one. That one was just a solid list, wasn't it?
List. Yes, very good. And what do we remember about lists? Are they unordered? Are they ordered?
Those are ordered.
They're ordered, right? And do you remember, does anybody remember if we can change them? Are they mutable or immutable? Are they changeable,
Mutable.
unchangeable?
Changeable. Yeah.
Yep, changeable. Absolutely. All right, cool. Keep that in mind. We're going to talk more about lists today. And then keyword arguments. Remember what data type this is?
Dictionary, wasn't it?
Yep, dictionary. That's what we're using right here. We do the key value pairs. Cool. And then we have our custom method here, the display details. And then similarly, we can look and see what we have in our main.py. And again, this is referencing the idea of files in directories, right? So these two files, our main.py and our classes.py, are in the same directory. If we look at the contents of this, I'm going to just scroll to the top of the page. So here's where I call the cat, which again is short for catenate, puts out each line. So here's the first line in our main.py. And what we did is from classes, so from this classes.py, without doing the full name of it, without the extension. We imported our car class, and then we can use it in our main.py with this app entry point. And we call it, so here's where we instantiate our class, and we send it some particular parts in key word arguments. That's what these are here, where it says model is celebrity as a string. And that gives us the ability to run this directly from the main.py and get our output as we expect from here. So that is again a display of a simple application that runs on its files in directories, and that's all applications are going to be. So I want to make sure that that is clear. Any questions about any of this before we move on?
I just had one question. I left a little bit early, but I went back and finished and followed you guys on the recording. And one of the last things you did was to swap in the add to our main file that if name equals main, and then print. But I was trying to figure out, why did it not do any of the other things that were on there?
Oh, these up here, these the container filler and all that stuff?
Yeah, the other stuff that we'd done previously.
Cool, good question. Yeah, so
Yeah.
so this whole top part, and that's great. So the last thing that I wanted to cover was the control structures that we talked about, right? So that's perfect question for that. So the first control structure we talked about was sequential. So when we do this call, the Python 3, and then the file main.py, that is going to initiate the default, the sequential control structure, which means it's going to read this file from top to bottom, left to right really fast, right? So it's going to start reading, and it's going to say from classes, import car. It's going to go over to this page, read the definition, come back. And then these are just definitions, similar to this class definition here. Like we could move these to yet another file and import them and not even have them written here, because all they're doing in these lines where it says def main and def compare nums and our loops here, all these things, these are just defining these functions, right?
I see that. Yeah.
And then once we get
Yeah.
into this application entry point and the conditional control structure is run, and this is checked to see if it is called directly, which it is in this call, we call this file directly, then these parts are where they actually call any of this, right? So the only calls that we make here are instantiating our class and then displaying the details from it. We don't call any of these commands.
So,
So that's-
the command is from classes import car, and then the output is that car. Is that
No,
Am I
no.
following?
So
No.
the import statement is just a way to make this car class available in this main.py file,
okay?
right? And then the call
and then
itself,
the last thing is if main equals main, then
right?
Okay.
Then after that, so inside of this app entry point block, we have our actual call to that car thing, so that when the
So,
application runs, it's calling it there.
But I still had if name equals main, my list equals 3,
Mhm.
but I don't say to print it, do I? Or display it. So, okay. Yeah, I got it. There's a lot of stuff going on that page. I was just trying to make sense of it.
Yeah, absolutely,
Yeah.
absolutely.
So
Okay.
Thanks.
in the whole main file,
Mhm.
like on the very end, like when you're doing like which command call,
Yep.
would it be possible like have a series of if or if and commands where like if certain metrics are met, then this
Mhm.
command will run or this command will run?
Yeah, you absolutely could. You could put all kinds of logic in there if you wanted to. Typically, what you're going to find is that there's not a lot inside of this. It'll just be, maybe one command, and then that logic you're talking about will be up here on the page somewhere, in like one main command or something like that. Like it'll be a main, and then all those if and sub commands that they might call will be wrapped up that way. So, but there's nothing really stopping you outside of convention. But again, that's kind of what we're going to get to in the class. It's really relevant today, is that there's nothing from the computer that's stopping you from doing that. So syntactically, no, there's nothing stopping you. Could absolutely do that. But as far as style goes and readability and maintainability, so like closer to the top of that scale, that's when you probably don't want to write it that way, but you can. Does that answer your question?
Yeah.
Cool. And again, so I'm doing it this way because I really want to make clear it is kind of not that convention, but I want to make clear that these are the parts being run. Again, kind of going back to Greg's question, I want to highlight that these are the parts that are actually run when the application is run. And I want to make sure that these are just seen as definitions where they're just being read and understood by the interpreter, but they're not executed until they're in this block. Good questions though. Any other questions?
My question is, how would I know, like the problem? Like computer programming is solving a problem, right?
Yes.
So the problem here is, I want to know what make and model of car I have.
Yeah.
And so the solution is this code. So I wouldn't know how to begin. I wouldn't know, like, how do I know how to which I don't know if you know where I'm going with this, but
I might.
how do I know what
might.
code to write?
Yeah.
How do I know what code to write?
How do you know
So
what code?
I wouldn't know. I can read it and it makes sense, but
sure.
I wouldn't know how to generate it from scratch.
Okay. So to that, I would say that's the part that takes practice, and that so like reading it is absolutely the first step of understanding, and then giving it a try and writing it yourself, and just trying to write it the way that you've seen it places. And that's what those algorithmic practice sets that I sent out was for, is that to give you exactly that, right? Because it's gonna
All right.
the more you do those sorts of things and use code to solve a problem, because that's exactly what those are. It has a specific, like the one we used in class as an example was get the domain name out of a URL. That's kind of a realistic problem. That's a real thing. Some of those problems are really silly, like the counting sheep or whatever, but there are useful tools and tricks in there that you get practice doing by solving those specific problems. And it'll just kind of become clear to you, like, again, I don't want to get too far ahead because we're going to talk about that today, like how we decide what we're going to do and which choices we're going to make. That's really exactly what we're talking about today, right? And how you know what code to choose and stuff like that. So that's exactly the topic of today's discussion. So it takes practice to really know, but there are some criteria that we use to decide. Does that answer your question?
Yeah.
Cool.
Thanks.
I have
Yeah.
a quick
I
question.
I had the exact same question, but I was alone and I didn't say it out loud when I opened up the Code Wars and I had
Yeah.
to multiply two things. I was like, I don't even know where to start. So
Yeah.
I
Yeah.
think and that's when it kicked. I got, oh man, you got to practice this shit.
Yep. You got to do it. And that's the thing. So like there are several times when I compared coding languages to human languages, they're not like human languages really, but there are some crossover, right? So one of the things, or like musical instruments, even you just got to practice or else you're going to forget how to do it. So, same sort of thing. Like you learn that dictionaries are really good at doing certain things. You just get good at knowing what those things are by using them a bunch of times and, kind of comparing it to lists and stuff like that. So the more practice, the better.
I have a question, Jeff.
Yeah.
Could you do like a problem statement for when to use a list, when to use a dictionary, such as I would like to list the number of 1987 vehicles in sequential versus I would like to know if there is a virtual vehicle made
Right.
in 1997 dictionary. And
Right.
I'm not doing it well, but I remember this something like this.
Okay. Okay. I think again, when we get to how we make the decision, we could frame it a little bit like that. Maybe make it clearer for you. In kind of general terms, I think just focus on. Well, no, we'll have to table that question, man. I don't have a real clear, simple answer until we get a little bit more into what those decisions are and really the differentiator between how these things behave. We talk about like something that's unordered versus ordered, and it really depends on what you're trying to do. Right.
'Cause
So
no one's ever told me, hey, can you write a code that gives me a list? No one says that. They
No.
always ask, can you tell us what's going on with this group?
Exactly. And so it'll be one of those things that as your data is flowing through your program, right? Data in the sense of the information you're tracking, that's what we're going to talk about later. That's like stored in a database, right? It's another sense of data we haven't talked about yet. As it goes in your program, you're going to break it up into these different data types. And sometimes it'll be convenient for your algorithm to put them into a list. And again, the decision that you make there will be based on if the order is important, if, the certain kind of operations you expect to do after that. And we're going to talk about that if you're going to be adding things to it a lot, or if it's going to be something that you're just going to take stuff out of or just read. And then again, if you're going to be looking things up out of it, it might be faster to do in a dictionary. So we'll get to exactly that sort of decision making as we go through the class today. Cool. These are great questions. It's like exactly on topic, but just not quite. It's just a little bit ahead of time. You guys are like way ahead of it. So anything else?
We know nothing and want to do everything.
Yeah, I love it. It's perfect. It's perfect. It's perfect. And that's actually kind of what is a really good segue back into what we were talking about. So we talked about these control structures and we ended with our while loop. And I remember that I guess we did the sequential control structure and then our conditional control structure with our if, elif, and else statements, which are really handy. And then we did our iterative control structure, which is our loops. So our for loop that goes through each item of something like a list. Remember, that's for item in the thing. And then our while loop that checks a condition to see if it's true. If it is, it enters the block and it runs this while as long as this condition is true, right? So we've got while the count is less than our maximum, which we passed in our container filler. We're going to increase the count by going up by 1, give us some sort of output that says we did it. And then at the end, we'll say it's full, right? So this is where we ended up last time. And what we're going to do now to start answering this question of how we make the decision, what we do, I'm going to show an example of refactoring this and writing it in a different way. But first, we're going to talk about a concept that's sort of what we're going to use to rewrite this. And that concept is also going to be something we're going to see later. And it's going to help kind of solidify a few of the things that we're talking about. So I'm going to go back to our slides real quick. I got like one more slide on this. So we're talking about the choices that we're making here. And so what we're going to do is talk about recursion as this idea. So anybody here know recursion already? Anybody have a concept of what this is? Could possibly define it for us in their own words before I try
looked
to.
it up when you first told me, but I didn't understand the people's
There are a lot of
definitions.
there are a lot of really unclear definitions out there. And I'll also give you kind of a warning. It's used in a number of different fields. So it's used in mathematics and linguistics really frequently. And then also computer science, so kind of the big 3 places it's used. But there's an example here. And yeah, Greg, thanks again. See you Monday.
It's like reuse of pieces, right? Something like that.
Yes, that's a good way to think
Yeah.
of it. Yeah. So this picture here is an MC Escher drawing, and it's recursive in a sense of using the same pattern sort of over and over again within itself. Recursion is something that we do. So linguistically, I'm a linguist again, and we do it every day. We're doing it all the time when we use language. It's one of the things that sets apart human language from animal languages. So like, for example, birds, they do all kinds of complex sounds and stuff like that, but we haven't seen them use recursion. They don't take those sounds and nest them within themselves the way we do with things like sentences. Think about a sentence. There is no defined length of a sentence. You could keep adding them into each other by saying, you know, I think that, or I heard that, or an and but, and all those sorts of things. We have a bunch of ways of just continually sticking sentences together. The process we're doing that with is recursion. So this is something that we all innately do. But as soon as you try to define it and you try to find somebody's definition of it, it's these crazy academic descriptions of something that we're really just doing. So we're going to use this in the computer sense. We're going to run through it, but I want to try to get, this is the definition I found that I thought was really good. So it's the repeated application of a rule, a definition or procedure to successive results, right? So when we did our for loop, we had a list, and at each one of those things, we did a thing. We did the same thing to each element of that list, right? That's not recursion. That's just going through and looping through something. Recursion is you go through and do something, something changes, you take that result and go through again with a piece of that procedure in computer sense. Does that make it some sense on what we're talking about? Still kind of confusing?
Maybe when we see it in practice.
In practice?
Yeah.
Okay, yeah. All right, cool. So good. Yeah, I want to lay the groundwork of seeing this name recursion, this idea that it's patterns within themselves, something that repeats, right? It's repeated application of a rule. So let's implement refactoring of this. Again, this while loop. We're going to refactor it. I'm going to go into the files to do that. I'm not going to do it here in V or anything. So I'm going to open up my files, but in a new tab. And I'm just going to go into my main.py, and we'll do it right here. All right. So let's go down to just a little bit underneath our while loop. And I'm going to refactor this into a recursive function. So I'm going to use a recursive function to do the exact same thing that this is doing. So I'm going to do a container filler. I'm going to fill up a container that's going to have a maximum. So the same principle concept is going to apply. So again, refactoring to the same result, but written in a different way. All right. So we do our define, DEF, and then I'll call this recursive filler. And this is going to take our maximum, just like it did before, except this time we're going to pass our count into it as one of the parameters that we pass in. We're not going to set it like we did in our earlier one where we did a while loop. And there's a reason for that. I'll show you. Maybe you could pick out the reason why. But for now, let's just go with this. We're going to put in our count. Okay. So when we do a recursive function, what we start with is what's called the base case or the exit condition, or like whatever it is that's going to stop this thing. And the thing that we're looking for, right? So we usually use just an if statement and we check for some condition. So anybody want to help me out, go out on a limb and see what condition you think we might want to check if we're doing the same function as we were doing before that we want to stop this with?
If count is more than maximum.
Okay. Do we want to do more then? Because if count is more than maximum, it's going to be bigger than the maximum, right?
Right.
And we want to stop it before it gets bigger, or else it'll be overflowing.
So equal to or greater than.
Well, if we do equal to or greater than, we could. I think it's this way you do that. But if we do that again, it'll. Well, yeah, I guess I would do it this way because we want it to stop here. We don't want it to go over. We don't want it to be greater than at any point. So we're just going to do is equal to, right? So the two equals, right? So if count is equal to maximum, this is going to be our X condition or our base case. And it's going to be the same as our base case from up here. We're just going to just say that this is what happened, right? That we have a full container. So I'm just going to copy this from our while loop, our regular container filler. The print container is full, and that's it. So this is our base case right here. So this is what happens when these two are the same. Great. Now, here, I'm going to move down a little bit, give us some space to see. And we'll say our else condition, because we only need one other condition for this. This is going to be where we do the recursive part. Now, I guess I'll jump straight to it, and then we can implement this piece right here where we give ourselves the update, because we do want to keep this, but I want to show you generally how recursion works and how a typical recursive function works with no other shenanigans going on. So to make this recursive, what we're going to do is we're going to call the same function that we are defining, recursive filler, inside of our else condition. And we're going to pass it the maximum, which is the same one that we used here, that we checked here. It hasn't changed, but we need it, again, to run this function again. And it needs another parameter because we need to put both these parameters in on every function call that we have. We're going to pass it our count, except our count needs to change. So we're going to make our count plus 1. So it's going to go up by 1, and it's going to run a second time. So this is a fully formed recursive function. That's it. It's not a lot to look at. It's really short, but the beauty of this, or I guess the way that this works, is when it's run, it'll run through this the first time. It'll take in its maximum. Let's say the maximum is 5, the count is 0, right? So it'll check it the first time, and we expect it not to match. So it'll come down to our else side, and it'll say, okay, just run this again with our maximum, but our count increased by 1, and it'll wait until this second one is run again. It'll run through a second time with the count being 1. And it'll, count is still not equal to the maximum. So it'll come back through here again, and it'll run it again, and it'll wait until it goes through and this condition is met. And then once this condition is met, it'll run back through and finish all those operations and give you that last result. So I'm going to refactor this just one more time so we have this piece in here. I'm just going to move the increment out the way we had it here, because that's going to be useful for us to see how this works and how it breaks. So I'm going to move the increment up here, and I'm going to take out this plus 1 here, right? So I'm going to move the increment like we did before, the plus, and then assignment 1, and then a print that we've added it using our function statement. So I just copied that stuff from up here, and then just change this to a regular call. So now there's our recursive function. So now we have a recursive filler. So let's try it out by putting it down in our app entry point. So I'm going to, another quick trick that's really handy in pretty much every text editor is if you highlight a couple of lines and hold down the control key and the slash, it'll comment out is what it's called, add a hashtag in front of those lines, and then the code editor won't read that when you run it. So it'll skip those parts, and those parts won't be run. That way you don't have to erase anything if you want to keep it for notes or something like that, but you don't want to run that part. And then I'm just going to add our recursive filler, but I'm going to pass it an actual maximum of 5 and count of 0. We'll save it. We go back to our bash console. I'm going to clear this up so that it's
What was
not
that
so
again? Control pound or?
Control and then slash. Hold down control, hit slash, and it could toggle comments on and off in a line or several lines. All right, cool. So we got the recursive filler with 5 and 0 saved, and then we're going to run our main and see how it goes. And now it ran exactly the same way we had it with our while loop. So it said the container has 1 item, 2, 3, 4, 5, and then it said it was full. Right. So that is operating the same way. We've refactored it to use a recursive function. Okay, so I have not yet answered your question that everybody has. Like, okay, why would we do this and what choice are we making, right? So we just saw that I can do it 2 different ways. And you're probably sitting there thinking, great, why do we just do that? Now we got another way of doing the same thing. Who cares? Let's try, I know last time we did this while loop, we broke this, and let's try breaking these things now in different ways and kind of see how it goes and what information we get back, because they're going to break in slightly different ways. So let's re-break this while loop. As an example, I'm going to call this container filler with just the maximum, except I'm not going to increment I commented out this increment on line 24. And I'm going to run that by itself. I'm going to comment this out, right? I'm going to run this with doesn't matter, R5, which is the maximum. I just want to save that just to refresh everyone's memory. Since that condition is never going to be met, we're going to enter an endless while loop when I run this. And it's going to keep saying the container has 0 items until I get to a point where it says your console is printing so much that it's interfering with other users, so it's been closed. Okay. So some sort of parameter stopped us. It was on Python Anywhere's side, and that's how it broke. Now this console's dead, so I have to go start another console. So I'm going to go back to my consoles, and I have none, so I'm going to start another bash console. now let's adjust this recursive filler to be some gigantic number. So I'm going to uncomment this, and I want to show what happens when this goes wrong. So I'm going to put some just like a whole bunch of zeros on what this is. And so what this is going to do is it's going to keep incrementing this number up until it matches this number, but this number is gigantic. So I just put a huge number of zeros on there. I'm going to save this. I'm going to run it, and let's see how it breaks. It's going to be different. Whoop. I forgot I had a new console going. Python 3 main.py. Cool. All right. So it broke, but this time it says a recursion error. Maximum recursion depth exceeded while calling Python object. And you see it went about 1,000 times. So when this container has 996 items, and then it decided to stop doing that.
I don't blame it.
Yeah, I don't blame it either. That's a lot of times to do it, right? And that also shows how fast it does these things, right? So it just stupidly did this as fast as it could until it broke. So before we get into what, knowing that, you know, the computer had to process this down into ones and zeros and all that stuff, what do you think this means? This recursion depth exceeded, maximum recursion depth exceeded. What is it? What do you think broke here? What was exceeded? Think about how computers have to process information. And we had it
too much RAM.
Yes, memory, absolutely. So what this is doing is called a stack space. Stack is a data structure that we're going to talk about shortly. But the idea here is that there is a certain set of memory set aside for this function to run. And each time it ran to the bottom of the recursion, and it had to go, let's go back to the code and look at it. Each time it ran down here to this point and had to go back up to the top, it would stack one of those calls in that memory space. And so that maximum recursion depth reached means that there was just too many of those calls stacked up in that space. So it exceeded the memory available for that. Does that make sense to everyone?
Yeah.
Maybe.
Okay, good. Getting some yeses, some kind of yes, and some maybes. All right. So the main difference here is that our while loop, although it broke when we didn't give it anything to get out of this condition, so the condition never changed. So this condition was always met. It broke because Python anywhere told us to stop being rude and stop taking up all of the space that everybody else might be using, right? This recursion filler broke because we exceeded the amount of something we had available. So it broke in different ways because different things are happening underneath the hood, right? So that's the main thing I want to show here, that they are two ways of approaching things. And recursion is a slightly more advanced way of doing things. You probably don't need recursion right away as a problem-solving tool most of the time. You probably get by with while loops for anything that's similar to this. But it's handy. It's good to know that you can use it. And sometimes it is a better solution. Again, depending on what it is you're trying to do, and with keeping in mind how they operate differently, right? And how they may break things differently. So any questions about this? Does recursion now make a little bit more sense now that we've run it once? Do you have any questions about it?
You break the recursive.
I'm sorry, what's that?
How did you break the recursive one?
This one right here? Yeah, so this was
Yeah.
because it just did too many calls, right? So that each one of these, which I don't even know how many this is a ton. So each one of these calls that goes through, so each time that it goes through, it's coming down here and just moving our count up by 1, and we started at 0. So the number of times it would have to go through here is huge. It would have to go through each one of these times to finish it. And every time it comes down to here, it stops and like keeps in memory the call when the count was 0. So the first count. And then the second time it keeps in memory when the count was 1. And then it keeps when the count was 2. And it just keeps stacking those calls up in the memory. And at some point there isn't any more space in the memory. So that's what breaks it. It says like we can't put any more function calls, but we still haven't gotten to this point yet. So that's what broke
What
it.
broke the while? What broke the while loop then? What was it? What made it different?
So this one was
There
because
no way out.
yeah, so there's no way for this to exit the loop. When I stopped incrementing here, this condition was always met.
Oh, I see.
And it never changed. So it just there was nothing here that would stop it and exit. And so when I go see if I can still see him. I may have to scroll up too far to see them. But you see here, it goes up by 1 each time for the thousands. Yeah, no, it stops. All right. So that, but then the other one, when it goes up, it's 0 each time because it does, nothing changes. When the while loop breaks, it goes up 0. It says 0 a million times. And then it's just like, okay. And again, it wasn't because we really maxed anything out. It was just taking too long because it was just constantly calling over and over and over again. And it would have kept going. But Python anywhere said, okay, stop being rude. You're taking up, we're like sharing some resources here. So then is your question?
Yeah.
Nice. All right. So we're going to get into more of those kind of the structures and the data of this, but I want to make sure that recursion is understood for a couple of reasons. First of all, it's really cool. I like it as an idea, but also because some of the algorithms that we're going to talk about here in a little bit are grouped as what's called recursive algorithms. So like they're a type of algorithm that you're going to run into, and they are built on this principles. They do whatever it is they do just over and over and over again. So if you just keep in mind that this is kind of what recursion is, and this is how it works, then when you see something that's talking about a recursive algorithm, this is what we're talking about. All right, so we're going to go into how we decide what we're doing here, right? So we talked about this as different ways of doing it. They break in different ways. There are a couple of different things that we use to decide what it is. I guess when we're relieving that tension, we're making that decision between human readability and computer readability. There's formal ways of deciding that sort of thing. Before we get into either of those exactly, I want to talk about some sort of like another theoretical thing that's really worth looking into. It's in the free coding resources down on the reading list. There are a bunch of really good things to read in here. I highly recommend pretty much all of it, but The Timeless Way of Building is one of the coolest things. So it's a book written in the 70s. It's an architect writing about buildings and cities and stuff like that. But this is a cult classic in software development. Everyone knows this one. And it's really cool because it's broken down into where you can read it in like an hour. It's not a novel that you have to read every single page. There's a kind of condensed, what do they call it?
Abridged.
Yeah, table of contents. The detailed table of contents is what they call it. So yeah, even though it's abridged. But yeah, so it's basically you could flip through that and it's meant to be treated as a manual. Right. And there's a lot of good pearls of wisdom in there and good approaches to design issues. One of his main contentions is that this is a natural process. Building is a natural thing, right? So that's also kind of the things that we're talking about here is something that we all kind of do innately. But out of this book, and one of the key ideas, we're not going to go through the whole thing, obviously, is that he talks about that your job in any design that you're doing is to design a configuration within a context that allows conflicts to resolve themselves. So there are going to be forces that come into conflict in any context in what you're talking about. And what you're trying to do is figure out the best configuration you can come up with within that context that will allow those forces to resolve themselves. So, kind of go back to the questions everybody was asking. It's like, how do we choose these things and what do we choose? That's our goal. Our goal is to figure out, given our context, how we're going to configure everything to make it work. So, think back to the scale. The human language is on one side, machine language is on the other. There are two main things that we use to decide which we're going to do. In references, we have this, what's called PEP 8. I've mentioned this before. It's a style guide for Python. And this is quite literally a complete layout of how you're supposed to write this with the idea being readability, right? So the guy that invented Python, he was talking about how code is read much more often than it's written, which I swear I didn't rip off from this guy. It's a coincidence that we think the same thing. It's just a fact, right? So this is just absolutely true. And the idea with this style guide is to make it readable for humans. So anytime you're trying to refactor your code, make it easier to maintain and read, you're going to be looking at a PEP 8 sort of thing that'll help you out, right? It'll help you out with the styles, the way you can write these things, all that. Now, the other side on how we decide if something is good for the machine to learn or read and understand is called Big O notation. Has anybody heard of this before? Anybody heard of Big O notation? No? All right. So
I heard of
Big O
it before.
you heard of it? Yeah, Anthony, I knew you would have. All right, right on.
I don't like it though.
Yeah, no, it's
I don't want to hear about it.
yeah, I was gonna say. So this is something that this is by far the most computer sciencey stuff we're gonna do in the class, and we're not gonna get super deep into it. This is a hugely deep topic. This is a place where you may run into a ton of math, but we don't need to use it. This is really to understand what is being talked about here, what choices are being made. And again, this goes to how we make the choice. This is the answer to the question of how we make the choice and what choice we're making, right? So if you're gunning to be an actual developer and you want to do this professionally, you can't avoid this. You got to learn this stuff. There are ways of calculating this big O, which we're going to talk about what it is. We're not going to talk about calculating in this course or any of those things. We're not going to get to that level of it. For everybody else, it's good to understand this. It's good to know what this is. And it's also when you're doing things like the Code Wars or Leet Code shows this stuff as well, or even the Free Code Camp, they have practice algorithmic challenge things in there as well. People will submit their answers in terms of this big O notation, right? So you'll see somebody might say, here's my solution, you know, time complexity is this, space complexity is that. So what I want to do with this piece of the course is make sure that we're exposed to the idea, we understand it at least conceptually, but we're not going to get super deep into it, right? So lots of questions. Let's make sure we're clear on what these things are. But I don't want anybody to get super wrapped up around the axle on this. It's not highly required for you to be successful at being able to code, but it is concepts that we should know. Right. So big O complexity chart. The O is from a German word Ordnung, which just means power, you know, orders of magnitude. And what this chart is showing is operations here on the y-axis on the left side. So there's the number of operations as it goes up. And then elements across here on the bottom is how many inputs into the operation there are. Right. So as the inputs go up, as the elements go up to the right, the number of operations go up according to these black lines. You see these black lines that are kind of moving up in different slopes. See if I can maybe zoom in a little bit. No, it's not zooming in any substantial way. Okay, so at the top of these, they have little markers. We don't need to memorize what these things are, but this little ON with an exclamation point is factorial time, and then we have exponential, right? Polynomial, logarithmic, linear time. The main part here, though, is you see this color coding, right? So this red is horrible. All this red stuff is really slow. So that's terrible. The orange color here is bad. So these are bad algorithms or slow algorithms, right? And then down here in the yellow is fair. There's a little sliver down here at the bottom is green, and darker green is good and excellent is that very bottom one that you're looking for, the constant times. And the main takeaway here is that this is what we did with our recursive function when we put in 5 as the maximum and it ran okay and it didn't take any unreasonable amount of time. That's somewhere over here on the left-hand side because recursion is very slow, right? So that'd be over here because we had very few inputs. But as soon as we put in a whole bunch of inputs, it was ramped up very quickly and it exceeded our memory space. So it broke over here. So this sort of thing is really relevant when the number of elements are large, right? So large organizations, this is a concern for them. Smaller projects, smaller things, you're probably not going to need to worry about optimizing your choices to this level. But again, it's going to be dependent on how many elements you have, how many inputs you have, how big the system is. Does this make sense? Anybody have any questions about this?
Inputs such as what do you mean by input?
So inputs like these numbers here, like, so these would be inputs, this 0 and this gigantic number, right? So when it was 5, then on our big O chart, it would be over here somewhere on the left-hand side of that because it's a small number of inputs. But then as soon as we add that ridiculous number of zeros and make it a gigantic number, then we're pushing that over to the right side on the elements. All right, any other questions about this before we move on? What this is representing, what this is showing us. Cool. All right, so now we can talk about data structures. As promised, this is what we're going to talk about today. So we've already talked about a few of these that are listed here. And on this chart, just to give a quick orientation, we have the data structures listed over on the left-hand side, right? So we have array, stack, queue. We'll talk about those. We've already talked about arrays. Do you remember what arrays are called in Python?
This?
Yes.
Integer.
Lists.
Lists.
Yeah, lists. Yes. So in general terms, that's an array, right? So we're going to talk about stacks and queues. We already kind of talked about a stack, as in the way that the function worked, but we'll talk a little bit more about that here. But I want to see right here where it says time complexity. We have average, worst. So this is kind of an average number, and the worst is the number of elements that are put into it, right? So worst would be more on this right side of the chart. Our worst case scenario was higher numbers of inputs usually. And then in this third row at the top, there's access, search, insertion, and deletion. So these are the things that you are trying to do, right? So what this is telling us is this is really the answer to the question everyone was asking, is how do we decide what we're going to use? It's like, okay, well, what is it you are trying to do? If you're trying to do something that a stack might work well for, and you're going to be inserting things into it, then you might want to look at a stack. So this is one of the tools that we would use for that. We can talk about, again, about a stack and a queue shortly and show what they are and show how it's different from a regular list. But this is one of the ways you decide is through big O notation on how long it's going to take. And time complexity is your CPU usage, the calculations that are done, the memory that it's using, and the space complexity is going to be the storage of these things and the implications for that. So again, you'll see solutions talked about in these terms of time complexity, space complexity. This is what they're talking about, and this is what they mean.
No one type suits all, right?
Exactly. And that's the thing, is that when we talk about like, how do you decide, it's really based on, again, the context that you're in. So the problem you're trying to solve, the system that you're working in, and what you're trying to do. So let's talk about real quick. I'm gonna go back over and do some examples of stacks and queues. We'll talk about first about like arrays and strings and like how things work. We talked a little bit already about how to add stuff to them. I'm gonna go back to the console real quick. Let's go through a few more examples of how these things work. And we'll talk about what's being done and why a stack or a queue might be better, right? So let's first talk about lists just as they are, arrays. So let's go to let's do a Python interpreter first and go straight in Python. And I'm gonna make an example list with just a few things in it. I'm gonna put a few strings, just A, B, and C, so we have something to play around with. So remember, a string is, or a list is square brackets, strings are in quotation marks. So I set our variable A to be this list. And then, yeah, I believe somebody asked last time, or when we talked about this when we introduced the first time, how you add things to it. So I mentioned a way of doing things if you want to add things to the back of a list is append, and if you want to take stuff out is pop. So if we do a dot pop, and again, there's a built-in method. And now we talked about classes, all things in Python are really classes. So there's like a parent string class that defines what a string is, and we made an instance of that here basically. And now we're just using the method pop that's built into it. And that'll give us the last element back, and we see that it's not in the list anymore. All right, so that's one way to remove something from the back of a list. And then append, we want to add that back or add something else, doesn't really matter. We use append to add things to the back of the list. So now we have that. Here, I'll move this up a little bit so we got some more space. And we can also do things like slicing lists. So we can give like the front of a list by saying A, and then when we reference by index, we give a whole number. We can give a range of numbers by using this colon, right? So if we want to use, say, give us the first thing that's in there, we give the range up to number 1. So it doesn't include the index that you give it, but it gives everything before that. And we can similarly slice the other way and give everything that's in front of that index. Right, so I did 1 colon, gave everything in there. We could do everything that's between it if we gave it 2 indices. You could give everything that's between it. But slicing, unlike pop and append, didn't change anything from there. It just returned the elements. So the list itself is still there. Right, so now we can add stuff to the front of a list as well. So we added stuff to the back with append. So we can add stuff to the front with this slicing by just doing 0 as the position that we put in there. And then setting it to something. Yeah, that's 0, right? And I'll set it to something. So we'll set it to Z, because why not? And now we see that that's at the front of the list. All right, so we can add stuff to the front. We can take stuff off the front. Now, the thing to remember here about lists is that this is being changed what's called in place, right? So Python does dynamically change the size of a list when it can. But if it runs out of space in memory, these have to be stored what's called contiguously, right? So it has to be all this has to be in a line in your memory somewhere. So if you keep adding things to the back of this, keep appending and making it longer, and it exceeds the space that it already had for around it in memory, and it can't be together anymore, the computer's going to pick the entire list up and move it to another place. So making changes to lists, sometimes adding things to lists, sometimes it's not the fastest operation because of that movement of things. So understanding that this is stored contiguously is an important part to remember about lists. All right, so we've just sort of that we can add things to the back, we add things to the front. A faster way to do this, besides, because again, you can dynamically adjust the size in memory to a certain extent, but a much faster way to do this is to tell the computer ahead of time that you may be adjusting things, but tell it which side you're going to adjust from. If you're expecting in your program to only adjust from the back, then you would use what's called a queue, or I'm sorry, you only add to the back and leave the front. You'd use a queue. And if you're going to add to the back and pull off from the back, you use a stack. So let's talk about those a little bit in our main.py. We're not going to go through implementing stacks and queues. I'm just going to show examples using some notes, just as some comments in here. That's not actual code because it's going to take too long to actually implement those things. And keep in mind, they can technically be done with strings, or with lists. So with the things that we just did with the popping and appending, taking stuff off the front, adding it to the front, those things can be done to achieve these. Is just keep in mind the lists are going to be slower to do it, right? So we're talking now about this difference between stacks, array, and queue. Right, so we're going to talk about what arrays and queues, or what queues and stacks are, and why you would choose one over the other. Right, so lists. Talked about those. Arrays, sorry, we talked about those as a list in Python. Let's talk about queue first. So a queue, Q-U-E-U-E, think about a movie theater, right? So we have a movie theater. Again, I'm doing this just in comments. We're not going to actually implement a queue. But a movie theater will have a line of people, right? So there'll be one person, and there'll be another person. They're waiting to get in, right? Person 2, person 3, and so on. And I'm going to put this in a list. Again, keep in mind, this can be done in a list, right? So imagine this. There's these double doors in the movie theater. When these doors open, people are going to enter from this side. So the first person that's in this line is going to come in. And as people come up before the doors are open, or even as they're open, they're going to enter this line from the back, right? So you have people coming in here, and this is called NQ, E-U-E, NQ, and DQ. Right? Okay, so there's people coming in one side, leaving the other side. And we think about this in terms of software and why you might want to do this in a program. So we talk about, again, Nathan, to your question, say, like, when would somebody ask you to do this? This would be something like, say, a customer service ticketing system, where it's relevant when people ask for service, what line they are in the queue. This is when you would do this sort of thing, right? And keep in mind, this can be done with an array. It's just slower on that memory level, right? So if you're expecting a whole bunch of people in your service queue, you may want to do a queue. Again, tell the computer that it's going to be a queue, that things are going to be coming in this side and going out that side. And it can arrange its memory in a way that'll make that operation faster than if you try to do this with an array. And this is called a first in, first out configuration, FIFO. You may hear that places. That's what this is. So coming in one side, exiting the other side, it's called a queue. And again, practical reason you may do that is anytime the order in which something starts or is dealt with or addressed or moved on to another level is relevant. Any questions about that, on what that is? Cool. All right, so the other thing that's definitely important to know, we've already kind of seen this, and I said we would get to it, is a stack. This is very similar to the queue. And again, it can be done with an array. We can implement a stack with an array. But imagine in, say, like a restaurant or something like that, we have a whole bunch of plates that are just stacked up on top of each other. We could do this vertically, but that's a little harder to draw when I'm doing it in text. And we have somebody on this side that's adding plates. Somebody that's like washing the dishes, right? So we got a dishwasher that's adding plates on this side. And then let's say we got somebody that's here that's taking plates off. It's like a, I don't know, like a line cook. Yeah, or somebody like that. And like somebody else is using these things, right? So somebody else in the restaurant that's taking off. So somebody's washing the plates, put them in the stack of clean plates, and then somebody's cooking the dishes, is taking the plates off and making dishes and sending them out for the servers to take them, right? So this is a stack. So this is where things are added to and taken away from the same side. So similar, so like we said before, we could implement this with an array. We could just use pop and append. So this top part could be append where we add stuff, and then pop could just be taking things off from there. But if we tell the computer ahead of time that this is going to be a stack because the program that we're writing is better suited for this, it will leave more variable space at the end than it would for an array, and it'll make sure that it has the space to address this operation in the back. In programming terms, right? So this is kind of a real world analogy. In programming terms, this is where you would do any sort of undo function. If you're writing like a text editor or something like that, when somebody hits Control Z, that's what this is doing. It's called a last in, first out setup, or LIFO. This is also when we read into our max recursion depth reached, it was this exact construction. So function calls, variables, storage, all of those use a stack as a data structure to set that up. That's how they operate. Any questions about those as concepts? And again, we're not implementing these because they don't look substantially different. It's not really that interesting. It would just take us a while to actually set this up and make it work. It's really not worth the time. It's something I would encourage you to do if you feel you want to make a text editor that has an undo function, for example, and implement your own stack. Say go for it, but we're not going to do it in class. Does it make sense though? Everybody tracking this?
I think so.
Okay.
Yes.
All right.
Ask me in 5 minutes.
So for example,
Is this kind of getting at the question that we've asked so far of like why you would do Warners? Because I feel this is the point I want to get to, especially Nathan, when you're saying like, you know, in somebody in real life, because now we have some somewhat real life examples, right? Like a customer service queue and at least an undo function and stuff like that. Like those are two things that could possibly happen, right?
Right. So a clarifying question would be, if they asked you to describe the difference between a stack versus a queue, you'd be able to say that a stack is something that gives you last in, first out, rather a queue. Well, a queue is a sequential list, and then, or no, first in, first out. What isn't that sequential or no?
Yeah, it's sequential. Yeah.
Okay, so there you go. So
it's gonna be first in, it's gonna be first in, first out for a queue, and then last in, first out for a stack.
I get the concept, and I'm trying to, like, when I'm asked questions and I'm trying to describe them to people in conversation, particularly with interviews and just
Right.
being able to articulate it. So, thank
Okay.
you.
Yeah, sure. And then, okay, any other questions about those before we talk about algorithms a little bit? So that was data structures, as promised. We those are some examples, as you can see on this list. We barely scratched the surface on all these different kinds of data. This is not a comprehensive list by any means, but there are a ton of trees, as you see on your trees, are an incredibly interesting, useful data structure. I recommend you take some time on. Hash tables we've already done. Anybody recall what we call hash tables in Python?
Comments?
No, that's the hashtag that we use for a comment. Close. Anybody else? I've kind of referred to it before as this. Oh, sorry, hash table. They're stored in key value pairs.
Dictionary?
Dictionary. Yep. So dictionaries are hash tables. So again, just like lists in Python are generally speaking, they're arrays. Anytime you see hash table, that's another name for a dictionary in Python. So hash table is one thing. All right, cool. So those are data structures. There's a lot more to learn about that. But the idea here is that they're going to perform differently depending on what operation you're trying to run, what it is you're trying to do with the thing, right? If you're trying to move it around, if what you're doing requires it to move in memory, or if it's something that can be dynamically sized, all those sorts of things. All right, so algorithms. We talked a little more about algorithms before, and this is something similar to data where it's used in a couple of different ways that could be really confusing, especially when you're trying to learn this stuff. The way that we've talked about it thus far has been in the general sense of we've defined an algorithm. We said, okay, it's a set of instructions. It serves a purpose. It's got finiteness, definiteness, all those sorts of things. And we've written some algorithms. We've done some algorithmic problem solving, hopefully, or you will go forth and do that this weekend. There is another way in which you'll hear algorithms, and that is in the sense of algorithms that are very widely used for a specific purpose and have a name. And they're specific processes and they solve a specific problem, right? So this list right here is a list of array sorting algorithms. So this is just named algorithms for how to sort arrays. So imagine you have an array that's unsorted, and here we go. There we go. Now I can zoom in a little bit more. Yeah, is that better? Okay. So now we got array sorting algorithms. And just like we had before, these can be measured in the same time complexity and space complexity as our different data structures can. And these, again, this is just sorting. So this is just for sorting arrays. There are all kinds of named algorithms. I think out of this list, if you want to know some, it's probably quick sort, merge sort, and bubble sort are probably the most frequently, maybe heap as well. But what's really cool about these, on top of like this whole thing, on top of just having this chart that shows what the complexity relative to other algorithms is, right? If you click on any of these, the quick sort, the merge sort, or any of those, it'll take you to the Wikipedia page that has these cool little diagrams, little animations. Whoa, no, I don't want to print that. What are we doing here? Sorry. I want to zoom in, not print. So it does these little, these cool little animations that show what this algorithm is doing, right? It has, you know, a lot more explanation of it. It's got the math behind it and all those kinds of, like, way more information you could probably ever want. But these are really helpful in kind of just visualizing what's going on when we're talking about different sorting and how it does it and what's going on, right? It's a way to visualize these algorithms. Definitely worth looking at. Another kind of algorithm that you'll hear a lot about, and they're not listed here. So these are sorting algorithms. And again, I recommend quick sort, merge sort, and bubble sort as ones you kind of understand how they work. Look into them. They come up a lot. Another one that's real frequently discussed and stuff to know how they work and sort of which ones are better are searching algorithms. So again, we're not going to go through implementation of any of these. That would take us way too long. But I do want to talk about the differences of them. The differences in them, and sort of what they'd be good for, how they work in broad terms, so that you, again, are aware of them and know which one you may want to choose depending on the problem you're trying to solve, right? So the first kind of search is called linear search, and that is very slow. It's very, very slow. So linear search is going through like a for loop. It goes through each thing in a list or in iterable or whatever, and it looks at each one of those things to find the item you're looking for. So let's say you're looking for a number, or say you're looking for a word in a dictionary or something like that, and it's going to go through this list and see if it's in there. So the reason this is so slow is, I guess, in the best case, if we talk about in big O notation, the best case scenario, which nobody really cares about, nobody cares about the best case scenario, is if the thing you're looking for is the very first item in that list, and then it'll go crazy fast, right? The worst case scenario is the thing you're looking for is not even in the list, and there are a lot of items in the list, right? So let's say there's 1 million items in your list, and the thing you're looking for is not there. You're gonna have to go through each one of those million things before you know for sure it's not there if you're doing linear search. So this is very, very slow search.
Is that what we do when we search for something in Windows?
I'm not gonna say, JD. Yeah, I'm not gonna say exactly how Windows does it, but maybe. Yeah, no, I don't know. I'm hoping it's a little more complex than that, but yeah, it could be. Could be. All right, so a next faster way of doing it that you'll hear a lot of reference to is called binary search. And that's, again, it's faster. It's not blindingly fast or anything like that. But to understand sort of how binary search works, it's good to have a concept of how this works generally without having to implement it or run it or run it or anything like that. Is what it's doing is splitting the thing that you're looking through in half. So if you think about, if anybody's using this analogy, actually becomes worse and worse as time goes on, because it's probably been a good 20 years since I used a paper dictionary. But if anybody thinks back to using a physical dictionary that you opened as a book, right? And you're thinking about, okay, I can, if I'm looking for a word that's in the front half of the dictionary, you may just open the dictionary in the middle and then start looking forward, and then maybe open it again in the middle and try to ratchet, kind of bracket in like I don't know if we have any artillery folks or mortarmen on the call, but you might use bracketing to kind of get in there. That's what binary search is doing. What it does is it takes, say, if you have an array, it cuts the array in half, and it uses in, which we've looked at before, which right here, right? So for item in This in right here is very common. It's not just in Python. It's something that's in pretty much every coding language. Oh, nice. Nice. Yeah, Josh Rice saying that your dad confirmed the Windows is linear search. Nice. That's why it's so slow. So, so what binary search is doing is it's going to cut the thing in half that you're searching through, and it's just going to see if the thing you're looking for is in each half, right? So if it looks in there, it's going to say it's in here or it's not. That searching for the presence of the thing without finding it is something that computers can do. So it's like, yeah, it's in this one. So it throws out the other half, and then it splits that thing in half again. And so this is a recursive function. Sorry, this is binary search is recursive. So when we talked about algorithms being grouped as recursive or not, this is one of those things that's recursive. So each time it goes through, it's going to cut the thing in half. So it's a lot faster than linear search because by definition, each time it goes through, it's 50% less that it's looking at. So it gets faster each time, right? So if you go again, if you have a million things, the first time you do it, you're knocking it down to 500,000. Then the next time is 250,000, right? And it keeps going like that until you find the thing you're looking for. So it's a lot faster than linear search. But there is a much, much faster way to look for things. And this is called hashing, right? So any kind of hash, this is one of the fastest ways to look for things when you're talking about search, right? So it's even faster. I won't say fastest because I'm not sure if it's the absolute fastest, but it's definitely faster. So hashing, again, so we actually just talked about this. A hash table is what?
Dictionary.
Dictionary, which means it has key value pairs, right? So this, if we use the analogy of dictionaries in more modern terms, if you look up a word now and you're looking up the meaning of a word, we're going to Google, right? We put in the word in Google and it just comes back with the definition right away. Now, I'm not gonna say that's what Google search. Google search is way more than hashing. Well, I mean, it's more than hashing, but that is an example of what hashing would be, where you just go grab the word itself out of the dictionary without looking for anything else. You just grab that key and it give you back the definition as the value. So it just goes straight to the one thing and pulls it straight back out. So it's by far faster than binary or linear search. That making sense?
But how would it know, like, where to find that exact word?
Because that's the thing, because it's just matching the key. That's the beauty of it. It doesn't matter where it is, because dictionaries are not ordered, right? So hash tables are similarly not ordered because dictionaries are just hash tables. So it's just matching the key, right? So it would have to be an exact match. It doesn't know that it's the word, but it doesn't have to look at any of the other things. It just matches that one key and gives you back that one value. So it just ignores everything else that's in there. It doesn't have to look at it at all. So it's that much. Does that answer your question?
Okay. Kind of.
Kind of. Okay. And again, we're not going to get to the depth of like how hashing works exactly, like how it's faster, because again, conceptually, it seems like it would have to look at other things to know which one is which. But just know that it's faster. That's the key takeaway here. If you want to look into read exactly what hashing is and how it's doing it and what makes it faster, I say go for it. But we're not going to get to that level of depth.
Okay.
But yeah, conceptually, it's just because it can look up that key immediately as opposed to going through and matching each one and seeing if it matches. So another thing that's just good to be familiar with and understand, we've talked about dictionaries in Python, but a really common form of a hash table that you'll find is actually from JavaScript, and it's called JavaScript Object Notation, or JSON. And this is just going to be key value pairs in square brackets or in curly brackets, just like a dictionary in Python. It's going to look the same, but this is one of those kind of standard files, data formats that you're going to see everywhere. So any database of information, usually any system out there, can spit out a JSON file with the database information that's in it. So if you want to move things from one system that's totally, written in, I don't know, in C or something like that, and you want to move it into your Python system, JSON is a way that you can exchange those things. It's a very commonly used hashing system. So I just wanted to kind of call that out while we're talking about our searching. And it's because hash tables are fast for searching. That's why it's so good for data purposes. Any questions about these and why we're discussing them?
You said JSON is a type of hashing.
Yeah, it's an example of hashing. Yeah. JSON is
Oh, okay.
a particular notation for, it's just key value pairs, but it's used all over the place, even outside of JavaScript itself. Like you'll interact with it in Python too. And then, so, I think, who was it? I think Nathan, you were talking about being able to sort of explain these things, especially when we talk about interviews. One of those things, anybody, again, who is, if you're serious about developing or any of those sorts of things, the way an interview might go is you get one of those algorithmic challenges that we sent out in the thing. Some of those, especially if you look at LeetCode, it'll show which companies ask which questions. You can see like specific questions they ask at interviews and stuff like that, and practice those. But one of the things they'll ask is, once you solve the problem, if it works or something like that, they'll say, okay, great, that works, but can you do better? And this is what they're talking about, right? So you generally just got to know if the choices you made are the most efficient choices, if you can do better and if you can't, and explain why, right? So this is what they're talking about. They say, like, can you do better? They're talking about in terms of this, in terms of complexity, the speed, the time that it takes to do things.
But if you know you could have done better, why didn't you have already done better? Like, wouldn't the answer be,
Yeah.
I've always done the best I can?
No. So like so the way it goes is they'll just say basically, so if you think about those practice problems that we gave, it'll be that kind of thing where they'll give you one of those to solve live on the spot. You know, they'll be like, okay, cool, we have this string. How many valid anagrams of this string can you make? Go. And you're like, okay. And then you have to, in what they call pseudocode, so it's not any particular language, you just kind of write out your logic on how you would solve that problem. And you just do the first idea that comes to your mind, basically. And the purpose there is for them to understand how you solve problems, your thinking process, and how you went about it, right? It may not be the most efficient thing that you find the first time, right? The first way you go about it might be using for loops, which, again, this way of iterating through things is inefficient. It's like beginner level. And I remember there's this guy that I worked with that was a manager of a development team. And when I was talking to him about interviewing, and he's like, yeah, let me put it this way, man. If I ask you to do something, you better come up with something better than a for loop. So again, knowing that this is not an efficient way of doing it, and knowing that there are probably better ways to do it, you may even on the spot just be like, all right, cool. Yeah, I'll just do a for loop and I'll solve it. And you solve the problem with a for loop. And then when they say, okay, cool, yeah, but can you do better? Be like, yeah, all right, I could, instead of doing a for loop, I could use a map or something like that and restructure this way. Or, instead of doing this while loop, you could do it recursively or something like that. And really the idea there, so to answer your question, JT, is a lot of times you're just going to answer and then look at it again and be like, yeah, these are ways I can optimize and improve. And that's, again, what they're looking for, can you come up with a quick solution? They don't expect the best solution, but then can you be critical of that in a logical way? And sometimes the solution came up with the first time is the best, and they just want you to know that, right? So they want you to be able to say whether or not it is the best solution and why, right? Say, like, can you do better? Be like, no, I really can't. That is the best solution. Or, yeah, if I don't use the
solution, I know.
Yeah. And that's the thing, that may not even be, if that's the best answer you got, that's totally fine too. That's the other thing, is that may not be, it may be true, but it'll also just show an honest account of how you understand things. Like, if for loop's all you know, man, use a for loop. It'll get it done. If that's not good enough for them, then again, they'll tell you. So that's cool. Any other questions?
Now you've got me thinking about the anagram problem.
Yeah. It's on that list, man. I think it's one of the ones. That's why I picked that, because I remember it being down towards the bottom of that. Those are fun. There's a lot of string manipulations in there.
There was in one of my college classes, there was a way to import data from like an actual website. Could you import like the Webster dictionary and then break the word down into string and be like, all right, rewrite it into all these words in the Webster dictionary?
Yeah, absolutely.
Yeah. Sweet.
All right. So next week is Thanksgiving week, so we're gonna have class Monday and Tuesday. We're gonna move the Thursday class up. And when we come in, we're gonna start building our web application. So we're gonna be in our web tab. And I set this up earlier today. just so that I can, let me zoom out a little bit. I think this is kind of jammed up everywhere. All right, there we go. So this is what it's going to look like when we get it set up. And again, just to refresh everyone's memory, we're going to be building a really simple website showing how to get some front end stuff in here. Not a super front end design class. We're going to have a couple of pages to navigate through. The main application we're going to build is a to-do list application where we could do our 4 basic operations of creating, reading, updating, and deleting things. So we can add a to-do list item like show life together. Let's give us some time to do that. Not a whole lot though. Submit, so then we can now read those things as the R in that create, read, update, and delete, or CRUD, right? So we can read those things. We just created something. I can update this, give myself more time. And it'll change that here. And we can delete things by just clicking this delete button. And we'll get a little JavaScript pop up that says, hey, you're sure you want to do that? And then we can delete those things. So we're going to start building this, start laying the groundwork for this in Python Anywhere starting next week. So if you haven't been doing all the stuff we've been doing up to now in the consoles here, you've been doing your own console, which is totally fine. You could continue to do that, but I really suggest that you start working on this on Python Anywhere come Monday. But with that, we can wrap up for tonight if nobody has any other questions. If you do about this or anything we've covered.
Mr. Stock, you're able to visit our consoles, right? So-
Yes, I can look into your consoles, I can look in your files. You stuck somewhere?
But yeah, kind of.
Okay.
So basically what I was trying to do was when you were going through the list, well, not the list, the list sliding for store continuously, I was trying to set that up and you had put in how A equals bracket A, B, C, or A equal. And
Yeah, this right
for
here.
some reason I can't get it to run right. It's just not, and I don't know if it's just my bash at all.
Did you get into the Python interpreter first?
Yeah, I thought so.
Okay. Because you might be doing this in Bash. Because you can set variables in Bash too, kind of environment variables using a lot of the same stuff, but then some of the stuff will break.
So you know
So-
what? Maybe I did not. Maybe I never
Yeah.
mind.
Yeah, if you're seeing a $sign and the tilde, then you're in Bash still. If you see these greater than symbols, then you're in your Python interpreter.
No. Yeah, I gotta be smarter than the computer. Okay, yeah, I messed that up.
Nice. Yeah, and you don't have to be that much smarter. I think the rule is 10%, so you should be able to hit that.
Did you give us homework?
No, there's nothing specific for this time. The same, again, work
Okay.
through that same list of things because there were like 20 problems on there. I doubt anybody's done them by now. But that is absolutely the best thing to do to practice on. And then again, next week when we get going, we'll be doing it together in class. I'll send out some documentation ahead of time if you want to get it going a little, maybe a little bit beforehand. But there will then be kind of homework if you don't do it in class with us to catch up on the app. But this practice that I sent out is what you should be doing now pretty much all the time that you've got a few minutes here and there.
Where are those
Code Wars?
questions?
Yeah, Code Wars and Leak Code. Yeah.
Okay.
I posted them in the Discord channel and the resources. They're pinned in the resources channel in Discord.
Okay,
And
problem
I
set. There it is.
emailed them out yesterday too for everybody.
Okay. Sweet.
Yeah. And don't hesitate to reach out if you get stuck. And we talked about, I know what JT, you and I talked in Discord. So we got a little thread in there about the second one. We talked about it a bit. Similarly, hit me up if you got a question and you're stuck. I have a solution to all of those. Some of them are my solutions. They're terrible, but they'll get you to the point that we can get you unstuck if you're totally baffled. But take a swing on all those. Those are good things to practice. It's mostly focused on strings and lists and stuff like that. That's going to be the majority of the time that you're going to be working with strings and lists. So it gives you really good practice. Daniel, to your question about how to choose, you'll really start hammering home what strings can do, what they're good for. Definitely refer to the just the documentation at Python. So there's this in the documentation where it says Python itself. They have really good docs about like how to do things. The documentation is really, really good for built-in built-in methods, built-in functions and stuff like that that Python can do. And all those things that we were doing here, like we did the append and pop and stuff like that, all these things about lists, like look up the list in the documentation and it'll have these things listed out on all the operations you can do. It'll really help you solve those problems as well. Cause then you could just, Python's really flexible. And it's got a bunch of cool stuff built into it. So if you're like, okay, cool, I want to like chop this list up. How do I chop up a list? You go look up things like slice. We didn't really talk about that today, but you can do, there's just a built-in, I think it's just the word slice. You could do things like that with lists and tell it where to chop it up and things like that. So practice, look at the documentation. That's kind of the homework.
Okie dokie.
All right, y'all. So nothing else. I'm available whenever, when we will be in class on Monday.
Right.
Thank
All right,
you.
y'all. Yep. Thank you. Have a great night.
Thank
I
you.
don't hear from you.
Thanks,
Have a
Jeff.
weekend.
You
Yeah.
too.
Have a good evening.
But
Good night.
All right. Take care.
Yep. Have a good one.